Chemical equilibrium, part 2. We're going to take a look at the relationship of Kp to Kc, the equilibrium constant expressed with pressure and the equilibrium constant expressed with concentration. We can say that Kp is equal to Kc multiplied by RT raised to the delta N power, where R is the ideal gas constant, 0.08206 atmosphere liter over mole Kelvin. T is temperature in kelvins, and delta N is the total number of moles of gaseous products minus the total number of moles of gaseous reactants. Let's see how we can derive this equation. Now, you won't have to be able to derive it yourself, but I think it's important that you understand where it comes from. So we could say that if we have this reaction, that Kp would be expressed this way. Now, the ideal gas law says that PV equals nRT. P is pressure, V is volume, N is number of moles, R is the ideal gas constant, and T is temperature. We can rearrange this and say that P is equal to N over V divided by RT, and then we can substitute in for moles divided by volume. Well, that would be moles per liter if you had units, right? That's just molarity. So P is equal to capital M for molar concentration, RT. All right, so let's substitute for P, let's substitute MRT into this expression for each one of the chemicals. So the molar concentration of chemical D times RT raised to the D power, and molar concentration of E times RT raised to the E power, molar concentration of A times RT raised to the A power, and molar concentration of B times RT raised to the B power. Now we can rearrange that expression, and in fact we can factor out the RT values, and we get that D, concentration of D to the D power times concentration of E to the E power divided by concentration of A to the A power and concentration of B to the B power multiplied by RT to the D plus E. Remember that RT to the D power times RT to the E power is RT to the D plus E power. And on the bottom, we would have RT to the A plus B power. If we multiply RT to the A and RT to the B, that would be RT to the A plus B. So now we can say that this expression is the same as Kc. This is the expression, the equilibrium constant expression, put together with concentrations. So that's Kc. We can take RT to the D plus E divided by RT to the A plus B and say that that's RT to the power of D plus E minus A plus B. So this would be the mole values for the products minus the mole values for the reactants. So we're going to express this as just delta N, the change in the mole values, the products minus the reactants. And we get this expression. Now, once again, you won't have to know how to derive this expression, but you should know that this equation comes from somewhere. And it is important to remember that R is used as 0.08206, and temperature has to be in kelvins when you do calculations with that. Let's take a look at a few quick examples of this equation. Let's say that we have a gaseous reaction like this, and this is a balanced equation. We have 1 mole of this chemical producing 1 mole of this and 1 mole of that. The number of moles of product are 1 and 1, so 2 moles of product, and the number of moles of reactants just 1. So the delta N would be the total number of moles of product minus the number of moles of reactant, so 2 minus 1 is 1. So we could say that this expression becomes Kp is equal to Kc to multiplied by RT to the 1 power. Or just Kp is equal to Kc multiplied by RT. Again, R is 0.08206, T is temperature in kelvins. and both Kp and Kc are unitless values. Okay, if we have this equation with all gases, notice that we have 2 moles of product and 2 moles of reactant. So the delta N would be total number of moles of product minus total number of moles of reactant. 2 minus 2 is 0. So Kp is equal to Kc multiplied by the quantity RT to the 0 power. Well, anything to the 0 power is equal to 1, so Kp is equal to Kc when the moles of reactant equal the moles of product. And if we have 1 and 3 more is 4 moles of reactant and 2 moles of product, we see that delta N, 2 minus 4, is negative 2. So Kp is equal to Kc multiplied by the quantity RT to the negative 2 power. Or Kp is equal to Kc divided by RT to the second power. Remember, when you have a negative power, that puts that value in the denominator. Let's take a look at a calculation using some numbers. Let's say that we have this reaction. It's a gaseous equilibrium, so we have all gases. And we know that Kc for that reaction is equal to 0.0952 at 227 degrees Celsius, which calculates out to be 500 Kelvin. Remember, you have to use temperature in Kelvin when we're using this expression. So let's plug into this formula to solve for Kp. Kc multiplied by 0.08206, that's the value of R, times 500, that's the temperature in Kelvin. And we don't have to put any units on this because Kp is going to be a unitless value. We take the product of these two and raise it to the second power, multiply that all together, and we get 160.3. No units for that.